How do we develop the theory of everything? An ultimate theory that completely describes all physical phenomena. A theory which unifies all interactions at all energy scales. You let that sink in a bit. It's kind of an overwhelming prospect. You might even wonder to yourself, can we do that? Well, where are we today? We have the standard model of particle physics, and this has been an excellent theory. It does a superb job of predicting phenomena such as nuclear beta decay. It also very accurately predicts the properties of new particles, such as you all saw in the news recently, one of the greatest confirmations of the standard model, the Higgs boson has been discovered. But the standard model is not a theory of everything. We can't link it to general relativity. Gravity does not appear in the standard model. There's a lot of questions about the model, a lot of why, and we know some pieces are wrong. So how do we go from this extremely successful theory to complete? So if you're designing a product and you want to make sure it works in all situations, or if you want to build a car and you want to make sure that you're not going to die if you get in a crash, what do? You test it. You do a crash test. So that's what we want to do. We want to actually try to break our standard model. And what I mean is, we want to look for weaknesses in the theory, the parts that we know that are missing. We want to make accurate measurements, and we want to look for the small deviations that signal a red flag that say something is wrong. That something wrong has to be new physics, some missing interaction or missing particle that doesn't have a place yet in our model. So the crash test dummy that we use here at LANL is the ultracold neutron. These are neutrons with extremely low energy and extremely low temperature. We can use the standard model to predict with very high precision the properties and the behavior of the ultracold neutron with respect to the 4 fundamental forces. For example, because of the weak force, the neutron undergoes a radioactive decay. And it's actually the simplest kind of atomic nucleus that undergoes this decay. And here at LANL, we measure the properties of the decay and the particles that come out and their angles. And this lets us test very precisely our understanding of the weak force. So when you take a neutron and you reduce it to these extremely low energies, something really interesting happens. Can anyone here dunk a basketball? Do we have any Olympic runners in the room? Okay, here's an easy one. Can anyone walk through walls? Of course not. Well, if you didn't raise your hand, congratulations. You meet the criteria to be an ultracold neutron. Ultracold neutrons are so low energy that they're sensitive to gravity. Most of them can only bounce about as high as I can reach. The highest energy ones go about as high as a basketball court or a basketball goal. You can outrun most of them. You can actually open the door to your experiment and race them to your detector. And the defining characteristic, if I take an ultracold neutron and I throw it at a wall made of something like nickel or copper, it won't be absorbed by the wall. It won't go through the wall. It'll bounce off the wall and be reflected back to me. So these properties actually make ultracold neutrons extremely convenient for experimental physicists like me. There are 3 main potentials that we use to control the ultracold neutrons. The neutrons can be reflected or accelerated by magnetic fields through a coupling to the neutron's polarization. They're sensitive to gravity. They can only bounce a few meters high. And they're also sensitive to materials. So most people who do neutron experiments, they use fast neutrons, a beam of fast neutrons coming from like a reactor or an accelerator that they have to build their experiment around. But our neutrons can be guided, they can turn corners, they can be stored in bottles. Instead of having a beam of neutrons, we can literally fill a bucket with ultracold neutrons and turn our accelerator off and do our experiment that way. So what do we actually do here at LANL? How are we trying to break the standard model with these ultracold neutrons? One way we try is by using the half-life of the neutron's decay. Because of the weak force, we can use this to very precisely test how well we understand. This is one of the most precise tests for how well we understand the weak interaction. And it's useful for a lot of other ways. This tells us how fast the early atoms were formed from the neutrons and protons in the early universe. Now the problem is, there's a bit of a scandal in nuclear physics now. We don't actually know what the half-life of the neutron is. It turns out, if you measure the half-life using a bottle of ultracold neutrons, you get an answer that's about 5 seconds shorter than the people who measure them from a beam of faster neutrons. It's as if the neutrons are animals in captivity. They don't live as long if you cage them in a bottle. So here at LANL, we're trying to improve upon more recent ultracold neutron storage techniques and learn from those lessons and make sure that the problem isn't the experimental technique. So here you can see ultracold neutrons in their natural habitat. Up on the right is where the neutrons enter into the experimental area, and you can go ahead and race them all the way down to the big bathtub that you see on the left. And here's a diagram that shows what that looks like. What we use, instead of a material bottle, we use a large array of magnets to reflect polarized neutrons, and this way they never actually come into contact with a material. And this way we can limit possible interactions with the walls so that we can store the neutrons for as long as possible. Even the shape of the trap has come into play into eliminating any possibility that neutrons can escape this bottle from any method other than decaying. The neutron lives for about 15 minutes. This bottle, if it weren't for that decay, would store them for about 10 or 15 hours. Another way we try to test the Standard Model is by looking at the charge distribution inside the neutron. Now the neutron is neutral, but you can imagine that you can have positive charges preferring to be on one side of the neutron, the negative charges preferring to be on the other side. The Standard Model tells us, because of the fundamental symmetries of the universe, that this charge should be almost perfectly even. So we're trying to look for, but we think there's some issue with, there are some concerns about that particular point in the Standard Model. So we're trying to look for an offset, this kind of offset in the charge inside the neutron. You can do that by applying magnetic and electric fields to rotate the neutron. If there's an offset in the charge, by applying a different electric field, you'll see a different kind of rotation. The experiment that we're designing has to be so sensitive, it can measure an offset the size of a human hair if the neutron were the size of the Earth. So with experiments like these, can we develop a theory of everything? Well, cars have gotten safer. We have seatbelts, we have airbags, and in a few years, cars are going to be driving themselves. If humankind has shown its achievements in innovation, it's certainly shown its achievements in breaking things. But innovations in breaking things is how we build confidence that our cars are going to be safe, our products are going to work, our Standard Model actually describes our universe. But will there ever come a day when the physicists of the world say, we've done it, at last, we have a model that describes all physical phenomenon. Our Standard Model, our theory of everything is complete. We're done. Well, I certainly hope not. Thank you.